Assalamu alaikum. Can you confirm that you can see my screen?
Yes, sir.
So it's a continuation of our practice problems. But if you remember, last time we had one example, the robot arm, yeah, which was this pendulum-like thing, and at the end we arrived at an equation of this form. And you see, although we tried to get rid of units, but there was still one thing which required to write the units, and that was this G over L. So you see this theta was dimensionless, this 0.034 is dimensionless, but you still had this G over L. The reason is this theta double dot. Yeah, although theta is dimensionless, but when you differentiate it with respect to time twice, time is physical, time has units, physical units. So that is why you need this G over L. So G over L is related to L over G, and if you remember L over G, the square root of it we saw already in simple pendulum. So if you remember, the time period of the simple pendulum was 1 over 2 pi and L over G square rooted. So this is clear that L over G square rooted will have the same unit as time. So what does that tell us? That if we divide the physical time by this quantity, the number we get from that will be dimensionless. That is exactly what we have done here. This is what we mean by non-dimensional time. So just to recap, if we have an equation for simple pendulum which looks like that, we see sine of theta has no units. So G over L is needed because theta double dot has differentiation with respect to physical time, and we now know that we can get rid of that time by defining a new time, tau, which is the physical time divided by some time, some constant time, and the units of these two will cancel out. So now it doesn't matter whether you are dealing with seconds or minutes or hours, whatever unit you are using, you know that tau will still have no units because they will cancel out anyway. So now, how do we get rid of the differentiation now? Or sorry, how the differentiation will change. So now if I differentiate theta with respect to time, t has units now. So I'll simply apply chain rule. So now d theta over dt is d theta over d tau times d tau over dt. Now d tau over dt from this equation, d tau over dt is simply that G over L square rooted. So which means that it will be G over L square rooted or d theta over d tau. You see? So now we go from differentiation with respect to physical time to differentiation with respect to non-dimensional time, and we have to multiply this factor. And if we do this twice, we have to apply this rule twice, and that's why you don't have that square root anymore. But G over L is still there. Now if you plug this in this equation instead of theta double dot, yeah, you will have G over L on both sides, and now the final equation has no units at all. Now this equation is different because in this equation, if I compare it with this equation, this has units because of G over L, but here that G over L had disappeared. Okay, so this is truly a non-dimensional form of the equation. So now in that example, this is what we ended up. But if I apply this method, because if I want to put the value of G over L, remember the value of G over L in that example was 3.7, and it was second to minus 2. So you could not get rid of this. But with this method, now you have a new form of the equation which has time non-dimensional. So you can just write this 32.7 as it is. Okay, as well as it is. think no. I think no, no. Wait a minute. This will not be there. You will not even have this 32.7. Yeah, because that has disappeared. Here you see 1 here. You don't see G over L anymore. So this G over L will be replaced with this 1. Yeah. So now this will be our final form. Yeah. So this will disappear and this will be intact. This will be intact. Double dot will be replaced with this. So I think I need to fix this. Okay. This was a mistake. Okay. We can now move on to the actual topic. This was a side note because you will need these such transformations whenever you don't want to see units in your final calculations. But now we get back to the energy methods. And the energy method we have been using so far, we have been using kinetic energy a lot in most of the problems. And it solves most of the problems for us. But now we want to combine potential energy as well. Yeah, because in complicated problems, just like the inverted pendulum last time, yeah, the last time we dealt with an inverted pendulum, there was a card and there was this pendulum, and you see it had a potential energy as well as kinetic energy. So so we need to be able to deal with such problems, and you can have springs and so on. So typically kinetic energy will have an expression like that. It can be more complicated if you have more units, like more masses and more inertias. And potential energy by definition is the work done on the system. On the system is very important. By what we call conservative forces. Yeah. So only when the force is conservative um, is what we call the potential energy. So you have to work against basically the some field. So mgy is one example. Yeah. So if y is some height to which you raise a body, the potential energy gained will be mgy. Similarly, a spring with constant with stiffness. No, spring. I don't know if it was called stiffness. I think it was stiffness. Yeah. K. You have the potential energy of the elastic potential energy takes this form, and if it is rotational, then you just have this T as a subscript. So and you can have similarly many examples. So this is not new for you. You know kinetic energy, you know potential energy, and only this is the new thing for you, that each potential energy can be seen. Each potential energy can be seen as some force working against some field, and that's why if this is the uh, field force, you need a minus sign because you have to work against that field, like work against the electric gravitational field, work against the electric field, and so on, and only then you call it potential energy. So in this statement, actually that minus sign is understood there. So now what if we add these two? Yeah, so we can call that mechanical energy, K plus V, and some people call it Hamiltonian as a fancy name, and this H and this H. So in the literature, rather than using symbol E for energy, you will use Hamiltonian. You may ask, okay, why are we complicating things? Actually, when you say energy, energy has all types. It's not just kinetic and potential. It can have thermal energy, it can have chemical energy. So all those different types um, is not what we mean here. We are only focusing on two types of energy, kinetic and potential. And that's why we use the symbol H. So now this is the important bit. This mechanical energy, if it changes, if it has to change, now where will this change come from? This change has to come from outside, from the outside world. Yeah, so it means that some forces or torques in the external world, they have to act on the system, and that is why we need work done. So we need some work done on the system by what we call the non-conservative forces or non-conservative torques. We will exclude conservative. Why? Because the work done by conservative forces or torques is already included in V. This is the definition. So you cannot add it twice because H has K plus V. So delta H will include the work done by conservative forces. So here you only need to include the non-conservative force work done by non-conservative forces. And if you divide both by small time, you can have a nice relationship that the rate of change of this mechanical energy is actually equal to the rate of change of work, and rate of change of work, is power. Yeah, so we can have this relationship. Now, how does this help? This looks complicated, but let me tell you that this will solve the most difficult problems for us. So let's say we start with this problem. You remember last time we solved this, and the method in the book was not very convenient because we had to we needed one free body diagram for the cart, one free body diagram for the pendulum, and then we needed to write force balance and x-axis for this, force balance x-axis for this, and then we needed moment balance and all these different things. So, and there were internal forces which had to be eliminated. So now why not try the energy method now? Yeah, because this system now has kinetic energy as well as potential energy. So let's write down the kinetic energy first. The kinetic energy, the first term is the kinetic energy of the cart, because the cart cannot bounce up and down. It can only translate left, right. So you remember this from point P right towards the right, this was our x coordinate. So half mx dot squared is the kinetic energy of this is the kinetic energy of the cart. This is the kinetic energy of the inverted pendulum, and because it is using Ig, so it only represents the spinning, and you use the word spin when it is about its own center of mass. So remember, if you look at the rotation of this rod, this can be seen as spinning about G combined with orbit motion, okay, about P. So if you look from P, you can think of a massless rod and all the mass concentrated at G, and then you can think of it like a motion in a circle. So that is one part, that will be orbital motion. But combined to that, you can also imagine spinning about G. So this is the spinning part. And that's why we are not writing IP, because IP would mean that we're also including the orbital motion. So that's why deliberately this is IG. So now you have spinning and translation of the cart. Now you need orbital motion, kinetic energy of the orbital motion of the rod, and that is simply the length. Now, how do you come up with this expression? Normally, you would expect something like this: half mv squared. But what is v? Yeah. Normally, let me go to the previous slide. And normally, when you write kinetic energy of translation, you simply say half mv squared. Now, because this is scalar, this is also scalar. So v squared means that v is also scalar. And that's why v must be speed. It must be speed. The problem here in this diagram is that we are considering orbital motion, and this orbital motion has this linear velocity, let's say v, and that v has two components. It has a horizontal component, let's say vx, and it has a vertical component vy. So when you say v, it is a vector, and this vector has two components, vx and vy. So now if you want to write the expression for the kinetic energy associated with this v, you cannot say half mv squared because you cannot take the square of a vector. So what you need to do, I told you before, there are two ways. You either say v dot v, but a much simpler way is this. Take the magnitude and then take the square. Now the magnitude squared is simply the sum of square of both components. So it's vx squared plus vy squared divided by 2. That is exactly what we do here. Okay, this is half, this is divided by 2, m is already there, and now this, if you remember, if you think about this, and actually we had this expression that x dot is part of vx that can be attributed to the motion of the cart, because these two bodies are attached to the motion of the cart will also give that motion to the rod, and the rod is rotating as well, so it is the part of rotation. So, and the minus sign, because this phi is going against x is towards the right, the horizontal component of that is towards the left, so that is our vx. So now you see that it is basically vx squared and this is vy squared. So now we have everything in place. The kinetic energy, let me recap it. The kinetic energy of this whole system is equal to the translational kinetic energy of the cart, translational kinetic energy, the spinning kinetic energy about g, spinning, and the orbital. And it's not just the orbital, it also includes the effect of translation on the rod as well, because the rod is translating as well as rotating. It's that combined translational kinetic energy. You can think of it as translational plus orbital of the rod. So that was easy. Now we need to have the expression for potential energy. Potential energy, if you look at the previous slide, it is mgy, okay? So it tells you how a particular mass has been raised, how much has been raised. So if the height is y, you have mgy. So basically, we need to know mgy, and what is that y? That y, in this case, is the vertical distance of the center of mass from the reference, which is p. So it is this distance. Now this distance y, is the component of L, which is vertical, and that is L cosine phi. Yeah, if this is phi, yeah, so this will be sine. If this is if this is L, you have to take two components. Okay, this will be the sine component, and this will be the cos component, because this is phi. So this L cosine phi is the length adjacent to phi. The component of L adjacent to phi, and that's why we have L cosine phi. That is our y. So we have potential energy. And don't forget that we are assuming that we are writing 0 here, and 0 only means that at point P we are taking reference 0. So this is not an absolute 0. In reality, you will have some initial some reference energy V naught, but that will cancel out anyway on both sides. I told you what matters for these problems is changes in energy, and change in energy, and that this reference will cancel out. So we can safely take that to be 0. So now you have both the expressions, the expression for kinetic energy, the expression for potential energy. Just add the two and you have this complicated expression. Now, no matter how complicated this looks, you need to just see that this H is a function of some quantities. So you see, you can see x dot here. So it depends on x dot, it depends on phi dot, and it depends on phi. And in some general cases, it can also depend on x. You don't see x here, but in some other cases, it will also depend on x. Now the point is, why do you think I have written phi dot and phi both, and x dot both? Because x and x dot There are two different quantities. This is position, this is speed. So speed and position are independent quantities. If you can recall from linear algebra, you cannot write x dot as a linear combination of x. If you could, then you would have seen this there. Okay. Similarly, you cannot write x as a linear combination of x dot. Similarly, you cannot write phi as a linear combination of phi dot, and you cannot write x as a linear combination of phi. Now this is important because in some problems, if you remember, although I don't have the slide here, but in some problems when we had, for example, the no slip condition, if you remember, no slip condition. In no slip condition, we had this relationship that v was equal to r omega or x was equal to r theta. Now, in this case, v and omega are no longer independent. Similarly, x and theta are no longer independent. So if we had that relationship here, yeah, this is a different problem. Let's say in this problem we had that simplicity. Then x will not be independent from phi, and x dot will not be independent from phi dot, and we would have only two quantities, either phi dot phi or x dot. Yeah, but here in this case we know that we lose that simplicity, so we have to include all the quantities. It's a function of x dot, phi dot. Now how do we use the previous slide? We need this. We need to take the derivative of this. So if you remember, you must have taken this course MVC. Yeah. So in MVC, if you have a function of two variables and you want to differentiate that with respect to time, for example, such that x is also a function of time and y is also a function of time. So what do? You say that, okay, the derivative of that function is the partial derivative of x, and then you say x dot, partial derivative of y, and then you say y dot. This is what you know from MVC, from multivariable calculus. So we will do the same here. H dot will be the partial derivative of h with respect to x and then x dot, which in this case is 0 because we don't have any dependence on x. Then the partial derivative with respect to x dot, and then the dot of x dot, which is double dot. Similarly, differentiation with respect to phi and then phi dot, and then differentiation with respect to phi dot, and then the dot of phi dot, which is phi double dot. So we will gather this expression on the next slide. So differentiate with respect to time and apply that. You don't call it chain rule, but it is actually the total derivative. I think it's called the total derivative. Total differentiation. So this lengthy expression you get. Now what you need to do here is to group. So group all the terms which appear as coefficients of x dot. I'll tell you why we need that. Yeah, why I'm focusing on x dot and not on x double dot, for example, or phi double dot or phi dot square. I'm only focusing on x dot. Similarly, I gather all the terms which appear as coefficients of phi dot. So now what I have done basically is that I have expressed h dot as some coefficient multiplied by x dot plus some coefficient multiplied by phi dot. Now what is the advantage of that? The advantage of that is that I know that this must equal to the power of the non-conservative forces or torques, and power I know, you know that power for translational force is force, non-conservative force times velocity, and velocity you know is x dot. Yeah, so force times velocity gives me power, and that power you know is equal to h dot. Similarly, for a torque, if I have a torque, non-conservative torque, that torque, if it multiplies angular velocity, which is phi dot, so torque multiplied by angular velocity will give me power. So power plus power. And because x dot and phi dot are linearly independent, I can match these. I can match the coefficients. Remember, you can only match coefficients in an equation from one side to the other when you have linearly independent quantities. आपको याद होगा जिस तरह आप partial fraction expansion में करते हैं, आपको याद है partial fraction जब आप expand करते हैं उसमें for example s होता है, s squared होता है, s cubed होता है, and you just match the coefficients on both sides. And that you can do here as well. So अब आपको समझ आ जाएगी कि मैंने ये grouping क्यों की है, and that grouping allows you, and because you can write the power as t times omega and f times v, and this minus sign is only a consequence of the fact that x is towards the right and f is towards the left, so they're opposite, and there is no such thing for t. T is counterclockwise and phi is also counterclockwise, so you have a plus and a minus there. But what is more important is this matching. So this minus f must equal this coefficient of x dot, and that gives us one equation for free, first equation. Now this is the equation which you would get if you apply Newton's second law. So you see, you got the equation which you get from Newton's second law by energy methods. And similarly, if I match the other two coefficients, this coefficient and this coefficient, they both are coefficients of phi on both sides, independent means that now you have the second equation, rotational form. So you get the two equations in a very, very short time, okay? Now there is only one catch here. The catch is we were simply lucky that we could gather all these quantities as coefficients of x dot. I mean, how this would have been impossible if, for example, here we had an x dot. So an x dot cannot be, for example, if you have x dot squared, you cannot say x dot times x dot and you say that this is a coefficient. No, coefficient mean that this must not have x dot. ठीक है, तो यहाँ पे चूंकि इसमें कोई भी x dot नहीं है, x double dot है लेकिन वो independent है, x double dot is independent of x dot. So ये हमें इसका मतलब ये है कि trial and error based है, and we have to be lucky if we want to solve questions in this way. This is not acceptable. Yeah, we don't want to depend on chance. So there is a more organized method. I mean, I started from this because this was simple to follow. Yeah, simply you add kinetic energy to potential energy, and then you take the derivative on both sides, and you know that that derivative has to come from some work outside. So the matching of coefficients solved the problem for us. But what if this is not guaranteed? Now, we should get even more from the energy methods. We need a method which is guaranteed to work. So let's have a few observations. Let's say I start from the kinetic energy, half mv squared. So if I differentiate this with the velocity x dot, or speed if we want to be precise, you differentiate this and it will turn out that you get momentum. So how to get momentum from kinetic energy? If you are talking about translational kinetic energy, it's simply the derivative, okay? And because K is the kinetic energy for the whole system, so when you apply this operator to K, this has to be a partial operator because you know K has theta dot as well and all the other things. So similarly, if you want the angular momentum, then you have to differentiate the angular kinetic energy, and that again is derivative with respect to theta dot, partial derivative, because K has both theta dot and x dot in it. Okay, one more thing, we are talking about conservative forces. So the forces applied by the field, and by that I mean gravitational field or electric field or any of these fields or spring, yeah, they all are restoring. So because we're not talking about the force you apply from the outside world, we are talking about forces that are applied by the field. So, and which give you the potential energy. So for example, Earth will apply a force of minus mg on you. So for example, if this is y and if y is by reference upward, so if you take an object, let's say from this position to this position, the force by the gravity will be downward, yeah, and because the reference is upward, so if you simply write mg, now we don't use vector notation here. If you say g, then you don't need a minus sign, yeah, because g is by definition downward. But if I simply write mg, now m is scalar and g is scalar, so how on earth do I know whether this mg is upward or downward? Because the reference is y for me. If I don't put a minus sign, I will assume that this mg is also upward. Yeah, that's what the plus sign means. But I know that the actual force is downward, so that is represented by a minus sign. This minus sign means that it is a force which is against your displacement. And this displacement, we define this upward because we want potential energy. You don't get potential energy if you go down. And the same is the case with the elastic energy of the spring. Elastic energy is half kx squared, and if you differentiate this with respect to x and with a minus sign, that minus sign will give you the restoring force. And it is the restoring force due to which it has potential energy. You should know the source. The source of gravitational potential energy is minus mg. It's not plus mg, because g is scalar and you need that restoring force. You go up, Earth will bring you back. You expand the spring and the spring will try to get back. You compress a spring and the spring will try to expand back. So it is all these restoring forces which give you the potential energy. So to go from potential energy to the restoring force, you need this minus sign and differentiation. And remember, this time you differentiate the potential energy function, and because the potential energy function has other variables, for that it will be the partial derivative, yeah, partial, and so on. So now you have a recipe. While in these slides, all the derivatives were positive, here these derivatives are still positive with a plus sign. But to get these derivatives, we need to put a minus sign because we need the restoring forces, restoring force of the spring, the restoring force of the gravity, and so on. And due to that, it makes more sense to work. So previously we were working with this quantity, kinetic energy plus potential energy, and we called it the mechanical energy. This was not very helpful, and we have seen it there, yeah, because we depend on luck here. There was no straightforward method of writing the equations. But now, when we replace that by a minus sign and we give it a different name, now this minus sign helps us in this way, that the derivative of the potential and therefore the derivative of L will have those conservative forces as well. And which means that the momentum can be recovered from the Lagrangian. We call this Lagrangian, okay? Just like this was called Hamiltonian, now you are calling it a Lagrangian. It's just the difference. So you get the momentum in the same way, just like before. So there is no difference in these formulas. You see they are one-to-one matching. But this formula changes, okay? This minus mg doesn't change. This minus kx doesn't change. This minus k tau theta, kt theta doesn't change, because that is how we need restoring forces. But the right hand side will change. Here you need minus sign because this was the potential energy. Now you subtracted the potential energy from kinetic energy. So the minus sign is now part of Lagrangian, which means that if you replace this V by Lagrangian, you will not need a minus sign because L text includes that minus sign. So now if the counterpart of these derivatives is now, you have these equations. Now if you look there, you don't need a minus sign here, you don't need a minus sign here, you don't need a minus sign here. This is just a short for the partial derivative, okay? So for example, the partial derivative of x is also written as fx. That's a shorthand. So you see that we got rid of the minus sign because we included that minus sign in the Lagrangian by replacing potential energy with minus potential energy. And now we have a very clean set of equations. They are the equations you get from Newton's laws, I mean translational, rotational forms. And if you see, you can understand this now. You have the derivative of Lx dot. What is Lx dot? Lx dot. What is Lx dot? This is Lx dot. And Lx dot is momentum. You know, in the Newton's second law, you differentiate momentum. You say d by dt of momentum. Yeah, and that is equal to the net force. So that net force can be broken down to conservative forces plus non-conservative forces. Non-conservative forces is there as before, and conservative forces, you know, can be expressed as the derivative of Lagrangian, just like this. Yeah, just like this. So conservative forces, you know, are these derivatives. So because this conservative force has to be on the right hand side, you only want to see non-conservative. So this conservative force has to go to the left hand side, and when you transport this to the left hand side, this comes with a minus sign. Remember, so this minus sign is not because of this minus sign. This minus sign is because you took this term from the right hand side to the left hand side. Yeah, and Lx, so it is Lx which is the conservative force. This is the conservative force, and that conservative force should have been on the right hand side. We transported it to the left hand side. Similarly, this conservative force, so this conservative force comes here, this conservative force comes here, and this conservative force, actually this conservative force comes here, and this was the gravity. We don't have a gravity term here in general. Let me just some more bookkeeping. So basically, this conservative force comes here, this conservative force comes here, and this conservative force comes here. Yes, and this minus sign is basically coming from this side. This minus comes from this side, and this minus from this side. So you see that before we even applied this method to an example, we know that we will get these sets of equations. So now you can expect that instead of relying on your luck, you will get these two equations as a direct consequence of applying these. So this will be the first equation, this will be the second equation, this will be the third equation. In our case, we don't have a second equation because there is no y, there is no bouncing. So we will get one equation for the x-axis motion and one equation for the rotation, yeah, phi. So get ready for that, and we are now starting it. So we go back to that problem, revisit it. We are now revisiting this problem, and this time we solve this by the more organized approach. So we start with the Lagrangian, which means I'm using this strange L because I don't want to confuse this with the length there. So this is k plus, instead of k plus v, we go with k minus v because we want that minus sign explicit. And this is the expression. And if you see now, this L is a function of x, it is a function of x dot, is a function of phi, and is a function of phi dot. So we gather all these derivatives. Yeah, so we first differentiate with respect to x, which is 0 because there is no x there. Then we differentiate with respect to x dot, and you see x dot here, so the derivative, and then you see x dot here, so the derivative. So these two gives you this derivative, and then you differentiate this with respect to time. Use your usual calculus. So this is your derivative with respect to time of Lx dot. Similarly, we differentiate with respect to phi, and you see that you can find phi here in this term. You see this is not phi, this is phi dot. Phi dot is independent of phi, so we will only use this term to differentiate with respect to phi. And similarly, differentiation with respect to phi dot is appearing here and it's appearing here, of course multiplied by that. So these two will give you this L phi dot, and of course you will also need to differentiate that with respect to time, and you get this from calculus. Now you have in place all the necessary derivatives. Yeah, so now you apply the first equation. You see, non-conservative forces along x-axis. Remember, we are just taking this equation as it is, no trick, no memorization, nothing. Yeah, you can just apply that. We will not need this equation because we don't have bouncing and jumping. So we need just these two equations. This is first equation, this is second equation. The only difference is that instead of theta, we will have phi. So you apply that as the first equation and then the second equation, and because you have all the derivatives there, it will just be an exercise of plugging values. Okay. Similarly, this will be an exercise of plugging values. You will see that, okay, some terms will cancel out, but that you can do algebraically yourself. For example, this term cancels out with this term because you subtract this from this. Yeah, you subtract this from this, so this will cancel out, and that's why these equations are much simpler than the mess here. Do you have any question in this problem? Okay, थोड़ा सा lengthy था. You do need to appreciate the power of this method, क्योंकि यही question जब हमने solve किया था last time. Let me just show you the lecture slides 20, and I'll just show you how difficult it was. Yeah, so you needed basically, you needed this, and then you needed this. Yeah, in free body diagrams and force equations. And because I left a lot of detail, so that's why you if you remember, you needed this formula. Let me show you. Yeah, you needed this slide there. We had to use this formula. Yeah. So, and the application of this formula is not simple. Okay. Just remember that we have a simple formula when there is non-accelerating axis. If the axis is non-accelerating, which means that if this AG is 0 and this AP is 0, and if it is accelerating, which means that either AG or AP is non-zero. But if we are only given AG and we don't have any other acceleration available to us, then you use this form. Okay. Now, if you want to write your equation through the mass center, then you don't need anything. Through the mass center will not include any linear acceleration because of the symmetry. Because you assume the body to be symmetrical, so any expression of linear accelerations around this g, they will cancel out and you will not see them in the final equation. But if you want to have these equations through a different point, let's say P, then you have two forms. If you have the acceleration of the center available to you, then you just need to write the distance from point P and AG. But if you know the acceleration, linear acceleration, not of the center but of some other point, then you have to decompose it into two components, and then you see that okay, one component comes here, and because it's a moment, so APY will multiply Rx and APX will multiply Ry. By Rx I mean the linear two components of R, the displacement between P and G. So, and you know, one is plus, one is minus, because this is plus because it has the same sense as IP, and this is minus because it has the opposite sense from IP, from my MP. Sorry. So applying this equation is easy only for simple problems. If you have complicated problems, you can replace all this complication by the energy method. एनर्जी मेथड में आपको कोई इस तरह की इक्वेशंस जो है ना लगाने की जरूरत नहीं है, आपको सिर्फ ये लगाना है एंड पे नॉन कंजर्वेटिव फोर्सेस आउटसाइड. Okay. Now, nobody asked me this question, that what do you mean by non-conservative? यहाँ पे non-conservative force, non-conservative moment. Okay. Similarly, here I am talking about work done on the system by non-conservative forces, non-conservative torques. तो कंजर्वेटिव वो है जो किसी फील्ड से आ रहा है, फॉर एग्जांपल ना ग्रेविटेशनल फील्ड, या इलेक्ट्रिक फील्ड भी वो जिसमें कोई डेरिवेटिव्स ना हो, टाइम रेट ऑफ चेंज. तो फॉर एग्जांपल मैकेनिक्स में बहुत आसान, मैं आपको एग्जांपल देता हूँ. इफ यू हैव अ फ्रिक्शन, अ सरफेस विद फ्रिक्शन, एंड इफ यू नीड टू अप्लाई फोर्स, एंड बिकॉज दैट फोर्स हैज टू वर्क अगेंस्ट द फ्रिक्शन, so यहाँ पे जितना भी आप वर्क करेंगे, that work can only increase the kinetic energy if you speed up, okay, or if you slow down, it will be a decrease in kinetic energy. So change in energy will, as a result of this is what we mean by non-conservative. Non-conservative इसलिए है कि this work cannot be recovered. अगर ये gravity against होता तो gravity आपको ये वापस दे देती. इसी तरह ये वर्क अगर स्प्रिंग के अगेंस्ट होता तो ये वापस आ जाता आपके पास. दैट्स व्हाई वी हैव दैट कंजर्वेटिव इज जस्ट अनदर नेम फॉर रिस्टोरिंग. यू कैन रिस्टोर इट. बट नॉन कंजर्वेटिव में फ्रिक्शन के अगेंस्ट जो वर्क आप करते हैं, ठीक है ना, मोस्ट लाइकली दे आर कॉल्ड नॉन कंजर्वेटिव. सो इफ यू नाउ लुक एट दिस, वी नीड दिस फोर्स because it is non-conservative. Yeah. The work done by F will not come back. Similarly, the work done by the torque will not come back. ये external torque है. तो ये जो है ना, यही फोर्सेस अगर किसी फील्ड से आ रहे होते कंजर्वेटिव से, तो ये फिर हमें यहाँ पे ना होते, ये फिर आप इधर ही इसी में शामिल कर लेते. ठीक है, इसी में. Let's move on to a problem now. So you have a person who pushes a roller of radius r and inertia mr squared by 2. So inertia दिया हुआ है G is what this point, let's represent this point by G, and let's represent this point of contact by P. So Ig is just given to be mr squared by 2, and Ip will be Ig plus, you need parallel axis theorem, which is mr squared. So if you add mr squared to this, you will get 3 mr squared by 2. Okay. Now values are also given. So the roller mass is given to be 800 kilograms and the roller radius is 0.4 meter. Now you assume that the roller does not slip. Okay. Now what does this mean? Does not slip. Does not slip means that this angular velocity is related to this linear velocity, which is x dot, and this is related by r. Now do not confuse this angle, like let's say this angle is theta and omega dot is theta. Don't confuse this theta with this phi, because this phi is fixed. This is a fixed angle which doesn't change with time, okay? So a common mistake will be to say, क्योंकि इस डायग्राम में थीटा नहीं दिया हुआ, आपको फाई नजर आ गया और आप कह दें कि नहीं ये थीटा जो ओमेगा डॉट है, सॉरी ये उल्टा मैंने लिख दिया, ओमेगा इज थीटा डॉट, और आप कह दें कि नहीं नहीं ये तो फाई है क्योंकि डायग्राम में तो फाई गिवन है, तो दिस विल बी रॉन्ग, क्योंकि दिस फाई इज नॉट इवन चेंजिंग विद टाइम, एंड इवन इफ इट वाज चेंजिंग विद टाइम इट वुड बी हैव नथिंग टू डू विद ओमेगा. ये तो आप एफ जो है ना ये चेंज कर सकता है कि अगर ये चाहें तो ये इसको ऊपर नीचे कर सकता है. बट हियर इन दिस क्वेश्चन वी नो, इफ यू रीड दिस क्वेश्चन केयरफुली, a person pushes force F at an angle to the horizontal. So this phi is different. Even if it changes with time, that must be something independently done. Now you are required to derive the equation of motion in terms of part A, rotational velocity, omega. So ये equation आपने लिखना है in terms of omega. Part B क्या है? You need to write this in terms of displacement. ठीक है ना? अब ये मैं पहले से बता दूं कि ये जो दो चीजें हैं ओमेगा और x डॉट, you know x dot is equal to r omega because there is no slip. So हमने अगर इन दो में से एक भी सॉल्व किया तो दूसरा ऑटोमेटिकली सॉल्व हो जाएगा. We don't need to worry. बाद में हमने सिर्फ सब्स्टिट्यूशन करना है. So okay, अब यहाँ पे we have a choice. If you remember, we had two forms. If this is our G, so writing an equation, a rotational equation about G will not help us. Okay, because we know that this roller is translating as well as rotating. Yeah? So if we choose point P for example, और point P पे हमें एक चीज मिल रही है कि it does not slip. इसका मतलब ये है कि यहाँ पे कोई स्लिपिंग नहीं है. तो जब यहाँ पे स्लिपिंग नहीं है तो यहाँ पे एक्सेलरेशन क्या होगा? AP. AP will be 0, and that means that APX is 0 as well as APY is 0. Jumping भी नहीं हो रही ना, कोई jumping नहीं है. So which means that if we use this formula, even if you use this formula, this APX is 0 and this APY is 0, and we still are left with a simple formula. On the other hand, if we use this formula, it looks simple because it has only two terms, and it is appealing as well क्योंकि हमें IG पता है mr squared by 2. लेकिन प्रॉब्लम ये है कि AG क्या है? AG is the acceleration of the center. तो वहां जाके कि सेंटर का एक्सेलरेशन वहां पे क्या है इस प्रॉब्लम में? The acceleration of the center, this is the center G, and by that acceleration we mean AG is the linear acceleration. Linear acceleration क्या है? X dot, क्योंकि this is moving at displacement x, so x dot is the velocity and x double dot is the acceleration. तो ये AG हमें इंक्लूड करना पड़ेगा. तो इससे बेहतर है कि हम ये about P कर दें. P में हमें पता है AP 0 है because of non-slip, so we will have a much simpler formula because AP is 0, और this is your MP. ये MP क्यों है? क्योंकि देखो ना, इस फोर्स का ये कंपोनेंट है F cos phi, और ये डिस्टेंस कितना है? मोमेंट आर्म R. So F cos sin phi times R. This is your moment. IP, remember, because it's MP, so it has to be IP. IP we already worked out to be 3 times IG, and that's it. और उसके बाद आप part B के लिए आप सिर्फ ये फार्मूला लगाएं, because x dot is equal to r omega, so आप जो है ना ये इसको चेंज कर सकते हैं. Or if you don't want this simple method, if you want to solve this directly, then choose the alternative form. You still go with MP, but this time you use IG omega dot or x dot. यहाँ पे क्या है? तो x dot IG की जगह plug करके you can still get this. But this is not helpful because you will still have to use this formula. For example, you have to write x dot is equal to r omega and x double dot is equal to r omega dot. तो ये आपको फिर भी लगाना ही पड़ेगा. तो जब आप यहाँ पे लगा रहे हैं तो why not use it right there? ठीक है ना? So this was just for your understanding. You don't need this. But even if I don't use this method, because this is complicated, even these two methods, these two steps can be simplified. It is still not simple enough. We can go for the energy method, which will simplify things. अब एनर्जी मेथड आपको पता है कब मुश्किल होता है, जब आपके पास काइनेटिक एनर्जी भी हो और पोटेंशियल एनर्जी भी हो. In this case, we don't need potential energy because there is no motion, there is no spring, there is no motion upward or downward. So we can simply go with a simpler version of kinetic energy, and that is you write the expression for the kinetic energy, translational kinetic energy, rotational kinetic energy, और ये IG है आपका. ठीक है? Because we have explicitly expressed translation, so we don't need to use IP or anything else. Now by this method of no slip condition, you can write this either in the form of x dot squared and you eliminate omega, yeah, omega is equal to x dot over r, or you can eliminate x dot and replace it with r omega, and then you will have this form. So there are two, these are the two alternative forms. Yeah, this is one form, and in that form you see that the effective mass can be worked out. Effective mass is 3m by 2. And if you use this form, the effective inertia is 3m r squared by 2. तो आपके पास क्या क्या चीज आ गई? आपके पास एक me आ गया और एक आपके पास आ गया ie. Now another thing which you can try is the, जिस तरह हमने gears में किया था. So write an expression for the input power W dot और ये नॉन कंजर्वेटिव है. ठीक है? तो अब यहाँ पे क्योंकि एक्सटर्नल है, आपको पता है कि वो जो फोर्स है इस फोर्स का सिर्फ ये कंपोनेंट जो है ना is giving you power. इसका जो ये कंपोनेंट है it's not leading to any motion क्योंकि it's balanced by normal force, so it does not lead to power. पावर के लिए मोशन का भी होना जरूरी है ना, because power is equal to force times velocity. तो जब velocity zero है तो power भी zero हो जाएगा. So that's why only this component of force is effective, and that's what we mean by Fe. But if we want to write the same power in the form of omega, x dot is equal to r omega, now this is the effective moment. So अब आपके पास दो pairs आ गई. You have Me and Fe, effective force, effective moment, and on the other hand you have Ie and Me, effective moment and effective moment of inertia. अब इस पे आप इसको आप यूज करें न्यूटन लॉ, सेकंड लॉ के लिए. सॉरी ये उल्टा मैंने बता दिया. If you use this as a rotational form of Newton law and plug the values, you will have your equation. And if you use this translational form of Newton law, you will this. You see those two equations you get, one in terms of omega, the other in terms of x and x, and you don't need any complication. You don't even need to write any moments. Okay. So just by using the energy and power, you solve the problem. Okay. Problem 3.34. Now this problem is based on an example which is 3.4.1, and we can just go to the previous slide. You know, it is 3.4.1. So we solved that example last time by working with this free body diagram and applying force balance and moment balance. So this is what we have been doing, but the only difference this time is that the no slip condition is not satisfied. In that example, we had no slip condition assumed, और उसके लिए हमें इवन ये भी चाहिए था कि जो है ना, this friction force F had to be actually in part C. We worked out. Let me just show you part C there so that you know what we are talking about. It was this example, if you remember. In this example, you see it is explicitly written that the cylinder rolls without bouncing and slipping. So this was part A, this was part B, and in part C we even had to write the condition required for the cylinder to roll without slipping. और उसके लिए आपको याद होगा कि that is only possible when the actual friction has not reached the maximum possible value. This is the maximum possible value. जब तक ये फ्रिक्शन उससे कम है, ये स्लिपिंग स्टार्ट ही नहीं हो सकती. जब ये इसके इक्वल हो जाए तो उसके बाद ये स्लिपिंग स्टार्ट होगी, और स्लिपिंग के बाद क्या होगा कि यू विल नाउ गेट इनटू द डायनामिक फ्रिक्शन, और डायनामिक फ्रिक्शन में फिर ये फिक्स्ड होता है फिर, ठीक है, एंड एट दैट इज विद स्लिपिंग. सो हमारे केस में अब इस एग्जांपल में we need to take the friction force, and that's why in this example we need the coefficient of dynamic friction. The coefficient of dynamic friction is given to you because you know that this force, this friction force, will have exceeded the maximum static friction. If you remember, ये plot था ना, applied force ये है और फ्रिक्शन फोर्स यहाँ पे है. तो जब तक आप एक मैक्सिमम वैल्यू जो कि m mu s times n है, जब तक आप इसको एक्सीड नहीं करते तो द अप्लाइड फोर्स एंड द फ्रिक्शन फोर्स बैलेंस ईच अदर एंड नो मोशन, नो स्लिपिंग स्टार्ट. लेकिन जब आप इसको पहुंचते हैं उसके बाद क्या है, उसके बाद यू हैव डायनामिक फ्रिक्शन एंड देन यू कैन मूव. सो हमारे केस में दिस F will be equal to mu d n, and the force balance on the y-axis, because we have no bouncing, it's still no bouncing, no jumping, so that net force is 0, and these two opposing forces must balance each other, so which means that n must equal mg cos theta, yeah, and F equals md or mu d, और n की जगह मैं ये वैल्यू प्लग करूँ, so it's mg cos theta. So that is my value of friction force. That is the value of friction force. Now I can plug this value in this equation, and that equation will read magx equals mg sin theta minus mu d mg cos theta. So I can now get rid of m here and agx, and then I take just g common, and I'm left with sin theta minus mu d cos theta. So that is the solution to the first part. We need to derive the expression for the translational acceleration agx. ये हमने कर दिया, ठीक. And now you also need an expression for the angular acceleration alpha. Angular acceleration alpha. तो एंगुलर एक्सेलरेशन के लिए आपको याद है, अगर ये पहला ये एग्जांपल होता, एग्जांपल के लिए वी डिड नॉट नीड एनीथिंग. एग्जांपल के लिए हमने सिर्फ इसी से कैलकुलेट करना था, क्योंकि आपको पता है वहां पे रिलेशनशिप होता है ओमेगा इज थीटा डॉट, नहीं सॉरी, omega, r omega is x dot, yeah, which is v x, or r alpha is ax. So you see, we get those kinds of relationship, but we can't do that here because there is only a slip applicable when there is no slip. Here, the slip no slip condition is not satisfied, so we have to work that out separately. So you have to write down the moment equation about G. The moment equation about G. So this mg will have no moments because it is passing through it, and this n will have no moment because it is also passing through it. Only f will have moment. So f times, this is r, f times r is the moment m about G, and f has this expression. So you just plug this value here, and this must equal ig alpha, क्योंकि about G you don't care about the acceleration, ठीक है ना. ये जो acceleration वाला मामला है वो उसकी जरूरत नहीं है क्योंकि you are writing it about G, you are not writing it about P. If you are writing it about P तो फिर शायद आपको वो बाकी चीजें भी करनी पड़ती. So you just plug these values. Alpha will be equal to fr divided by ig, और f की जगह आप ये वैल्यू प्लग करें, so you are left with mu dg r cosine theta by ig. Okay, now in this example, regardless of whether you are dealing with this example or with this problem, in both cases you see something interesting, that ig is not given to you. ig को हम जरा देख लेना कि ig कहां से मिलेगा मुझे. If I go with the with this table, this disk can be modeled either, because this disk is cylindrical, so ये असल में ये मैंने यहाँ पे नहीं करना था. You have to bring it to the, so यहाँ पे करना था मैंने. So there are two cylindrical shapes, this one and this one, and this one as well. Yeah. So अब हमारे पास जो रोल है, सिलेंड्रिकल जो व्हील है, उसमें चूंकि उसका थिकनेस दिया नहीं है, so this is the case when the length, sorry thickness नहीं, length जो है ना उसका वो सिग्निफिकेंट हो, तो इसका मतलब ये वहां पे मॉडल हमारा नहीं बनेगा, ये भी नहीं बनेगा क्योंकि इसका डायमीटर सिग्निफिकेंट है. सो दिस इज द राइट मॉडल. और यहाँ पे आपके पास जो थिन डिस्क है उसका एनर्जी क्या है अबाउट द सेंटर, हाफ mr². तो यहाँ पे अगर हम ये लिख दे कि इस एग्जांपल में if I am to work out this ig, that ig will be half, और इसका मास मुझे गिवन होता और r गिवन है mr². ठीक है ना. वो अलग बात है कि इस क्वेश्चन में he has not tried to give you that piece of information. And remember we are talking about the rolling cylinder. एक और रीजन भी है कि हमें नहीं पता कि इस रोलिंग सिलेंडर का ये जो आउट ऑफ द पेज या इन टू द पेज वाला डायमेंशन कितना है, तो अगर वो सिग्निफिकेंट है तो फिर इवन ये फार्मूला भी गलत हो जाएगा. ठीक है ना. फिर आपको जो है ना, फिर आपको ये तो डेफिनेटली गलत है, ये तो कभी भी नहीं होगा, लेकिन मे बी यू हैव टू यूज दिस फार्मूला, दिस वन. आपने देखा होगा जब आप दीवार पे पेंट करते हैं, तो दीवार पे जो पेंट करते हैं तो वो जो रोलर होता है वो उसका एक सिग्निफिकेंट डायमीटर होता है और सिग्निफिकेंट लेंथ उसका है. सो उसका फिर है हाफ m, वैसे इसमें भी हाफ ma² ही है, the formula is not very different. Sorry, interestingly this formula and that formula is not very different. Okay, very interesting. But in the final problem of this lecture, problem 3.35, although he is not explicitly saying a hoop, a rolling cylinder, instead of a rolling cylinder, you see this hoop. Hoop is actually a kind of ring which is empty at the circle in the center. So, but anyway, you are given the mass and you are given radius, and it starts from rest and rolls on an inclined plane. So, बिल्कुल उसी प्रॉब्लम की तरफ हम जा रहे हैं. रोलिंग सिलेंडर की बजाय हमारे पास हुप है, inclined plane है, radius है, mass है, and it starts from rest. The only difference you see that this time you have been given the value of Ig, which is mr squared. तो वहां पे हम गेस करते रहे mr squared by 2 हमें मिल रहा था क्योंकि ये सॉलिड था, यहाँ पे ये सॉलिड नहीं है, ये mr squared है. ठीक है, for whatever reason he is providing you with that value. इसके अलावा अगर आप स्टेटमेंट पढ़ लें तो इसमें और एग्जाम्पल 3.41 में कोई फर्क नहीं है. If I go to example 3.41, अब नोट कर लें, सिर्फ ये IG नहीं गिवन, अदरवाइज देखो ना, ये वही स्टोरी है. मास, रेडियस, डिटरमिन द एक्सेलरेशन ऑफ द सेंटर ऑफ मास. इसकी एक्सेलरेशन हमें चाहिए थी AgX, और एंगुलर एक्सेलरेशन भी चाहिए थी अल्फा. And assume the cylinder rolls without bouncing and slipping. Use two approaches: moment about G, moment about P, and obtain the frictional condition required for the cylinder to roll. अब ये exactly वही चीज उधर repeat हो रही है. So this is maybe a practice for you, कि just by changing the language, it doesn't mean that you change the problem, it's still the same problem. ये सारे parts वही हैं, देखो. एक part C भी वही है, frictional condition. This is the only thing that is different. ठीक है ना? इसका मतलब ये है कि you can use those results as it is. You don't even need to resolve this. अब उसी प्रॉब्लम में जाएं. So इसका मतलब we can now go to that slide and we just use the results. So let's say हम पार्ट ए की तरफ आते हैं. पार्ट ए में हमारे पास the expression for AgX was जिससे एक्सप्रेशन, इसमें आप f को एलिमिनेट करेंगे, जारी बात है. You will divide both sides by r, so r will cancel out, and it will be alpha divided by r, and that will be Ig alpha is Agx over r squared, and you plug this there and you will have some very interesting expression for Agx. और उस एक्सप्रेशन में Ig जहां पे भी आता है उसकी जगह आप रिप्लेस कर दे mr squared, not by 2 but mr squared, and then you are done. Okay, part B में वही है कि instead of writing the moment equation about G, you are to write it about P, and then of course you will solve this. You see, maybe we can try this. Agx will be equal to r mg sine theta divided by Ig divided by r plus rm. Yeah. Yes. So अब यहाँ पे मैंने क्या करना है कि Ig has to be replaced with mr squared. So this will cancel out there, and this r will cancel out here, and m will cancel out there. So I'm left with g sine theta divided by 2. 1 plus 1 is 2. Yeah, it was that simple. And part C, no slip condition. So we had F equals म्यू एन एस, और यहाँ पे आपने सिर्फ ये करना है कि आई जी की वैल्यू प्लेस करनी है एम आर स्क्वायर्ड. So r squared will cancel out with r squared, and you are left with agxm. So which is mg sine theta over 2 must be less than mu s n. Yeah, and that n of course is mg sine theta. Sorry, mg sine theta. So sine theta cancel out, mg cancel out. So mu s must be greater than half. Yes, mu s must be greater than half. Now this was not easy in this question क्योंकि इस क्वेश्चन में IG की वैल्यू नहीं पता थी. So maybe you should see this just as a practice session. So we are done with today's lecture. If you have questions, we still have time left.